Hey everyone, I'm going to try this again. I'm going to make the video myself and hopefully I can kind of slow it down a little bit to make sure that things make sense. But to do that, I'm going to also probably cut out a few things. So I'm going to start by cutting out this derivation of e. If that was done in the first video, I honestly haven't watched it. If it was done in Miss Major's video, then feel free to look at that to understand this. But this just kind of gives you more information as to what e is. Okay. So when a logarithm whose base is e, we call that a natural logarithm. So rather than writing log base e of a, we use the notation natural log. Now, why they write it ln as opposed to nl, I don't know. All the properties for logarithms that exist for bases other than e will also exist for natural logs. Okay, so last time you might remember we were looking at a log expression and we had talked about if we couldn't rewrite this as 3 to some exponent equals 20, then what we could do is use this change of base formula that says you take the log of your argument and divide it by the log of your base. And doing that on a calculator, I'll go ahead and do this real quick. So log 20 divided by log 3. Calculator gives me 2.727 when rounded. Well, you can also use the natural log button. So it looks like ln on the calculator, and it's usually on the button that has an e to the x above it. And if I did natural log of 20 divided by natural log of 3, I'm going to still get 2.727. Okay, so that's just another way to do the same thing. And you guys did a really good job on this on the last IP, so I think you kind of see what you would need to do to figure out these. Okay. So I'm not going to worry about how to do these. Just know that your other option is you can use the natural log button and you'll still get the exact same thing. Okay? So for summary's sake, if I want to find a value for log base b of a, I can either do log of the argument, so log a over log b, or I could do natural log of a over natural log of b. So these are called change of base formulas. Okay, and they both give us the value of this logarithm. So you were asked in your IP to do some questions where you had to solve some logarithm equations by first rewriting as an exponential. So if I'm looking at a problem like this one, I would write this as 9 to the negative 2/3 equals x. And for simplicity's sake, I'm just going to put 9 to the 2/3 on my calculator. Not 2/3, but negative 2/3. Calculator gives me 0.231. Okay, and we're just going to leave our answer like that. Okay. For this one, natural log of 3, just remember this is the same as saying log base e of x equals 3. So to write this in exponential form, you would just write e to the third equals x. And then on your calculator, remember that e to the x thing is above the natural log button. So now all I'm going to do is just type second and then the natural log button. That activates my e button. And then type 3, and that tells me that e to the third is about 20.086. Okay. For the next one, I'm going to write this as 3 to the negative 3 equals 2x plus 1. Well, we should know that 3 to the negative third is 1 over 3 cubed, which is also known as 1 over 27 equals 2x plus 1. If I cross multiply here, I'm going to get 54x plus 27 equals 1. So I'm going to get 54x equals negative 26. And let's see, negative 26 54, so I could divide by 2, and I'm going to get negative 13 over, let's see, 54 divided by 2, why am I not, 27. Okay, so the answer for x is negative 13/27. Okay. All right, the next one, log base 20. So this is saying 20, this one's a little bit different. This one is saying 25 to the x equals 5 radical 5. Okay, so for this one, the method that we just did isn't going to be helpful. What I am going to do is think of this, so I'm going to think of this as log of 5 radical 5 divided by log 25. And we'll let the calculator do this. So I'm going to take log of 5 times square root of 5 divided by log 25. Calculator is going to give me, actually, it's not even approximately equal to, it's exactly equal to 0.75. Okay. Next one, same idea. I don't want to write this as 2 to the x plus 2 equals 9 because that's not going to be helpful, but I can make this side just be log 9 over log 2. And the calculator, when I do that, gives me 3.170. And that'll equal x plus 2. So then I just subtract 2 from both sides. And I get x equals 1.170. Okay. This next one, remember when you see natural log, that's saying log base e of x plus 3 equals 5. So this is saying e to the 5th equals x plus 3. I'm going to use my calculator for e to the 5th. Calculator says 148.413. Okay, so then subtract 3 from both sides, and we get 145.143 is equal to x. Okay, so some of these equations you can write in exponential form. Some you'll use your change of base formula to help you figure out the value that you need. So two exponential bases, or expressions rather, can be multiplied only if their bases are the same. Okay, and in that case, what do we do with the exponents? Well, so this is saying if I have a to the x times a to the y, I'm going to get a to the x plus y. So you add the exponents. And if they were divided, so if I had a to the x over a to the y, then we should know that we would subtract those exponents. Okay. A similar relationship exists between logarithmic expressions that share the same base. So let's look at log base 3 of 9 plus log base 3 of 3 and log base 3 of 27. Well, hopefully you know that log base 3 of 9 is 2 because 3 squared is 9. And log base 3 of 3 is 1 because 3 to the first is 3. And when we add those, we get 3. Log base 3 of 27, so 3 to what power makes 27? Well, that would be the third. So these expressions are equivalent. What do you think I would have done to the 9 and the 3 to get this 27? If you were saying, oh, I multiply them, you would be correct. Okay? Likewise, on this one, if I have log base 2 of 32, that's the same as saying 2 to the 5th is 32, so that means that's 5. And log base 2 of 4, so 2 to what exponent makes 4? Well, that'd be squared. 5 minus 2 is 3. Log base 2 of 8, so 2 to what power makes 8? That would be the third power. So, what could I have done with the 32 and the 4 to get this 8? If you said subtract, or divide them rather, you would have been correct. Okay, so using those ideas, we're going to come up with our first two properties for logarithms. If you have logs that have the same base and you're adding two separate logs, then you could condense this into a single log by saying log base b of m times n. Okay, so that's going to be what I call the product property. Okay, and same thing with natural log of a times natural log of b. You just do natural log of a times b. Okay, so if logs have same base and are added, you multiply the arguments. Okay. And the next one, we saw if we were subtracting the logs, we could divide them out. So this would be log base b of m divided by n, or natural log of a over b. So you just, if logs are subtracted, you divide the arguments. Okay? And I call that the quotient property because you'll be doing division. Next one, log base b of b to the n. Well, if you look there, you'll notice that this is saying b to some exponent equals b to the n. Well, that just means that this has to equal, x has to equal n. If I did natural log of e to the n, that's saying e to the x equals e to the n. Whoops, I meant to make that say x there. So that means x has to be n. So what this is saying is, oh, I didn't mean to make that x. What I meant to do was say that the answer to this is just the n. So these are the inverse properties. If you have log of a base and then this thing is a base to an exponent, the logs and the base cancel. Natural log always cancels with e. Okay? All right, now looking at this next one, so if I look at log base b of a to the n, so if I were to say log base b of a to the n, if I set that equal to x, that's saying b to the x equals a to the n. Well, how in the world do we do that? That one's not going to be quite as obvious. So let's think of another way to approach this, because right now this is like, what does that mean? So what we're going to do instead is we're going to think of this as, so this a to the n, so we're going to think of that as a times a times a times a, right? So we have log base b of a times a times a times a bunch of different times, right? And so if we apply this first property here in reverse, if I were to go from the product to separating them out, this would be log base b of a plus log base b of a plus log base b of a plus, we're going to have that n times. So this is going to be n times log base b of a. So your exponent basically moves to the front as a product. Okay, and I call this power rule. And same thing here, this will be n times natural log of a. So if I were to put this into words, what I would probably say is something like, let me get all this erased here, something like exponents get multiplied to the logs. Okay? And then the next one, we've already seen there are two options for this. So we'd say log a over log b, which is the same as natural log of a over natural log of b. So this is what I call change of base. And then this one, if we look here, when we have log base b of b to the n, if you have b to the log base b, those also cancel out, same as e to the natural log. So those are just going to equal a. And those are also inverse properties. Okay, so what I'm going to do is I'm going to stop this video here, and then I'm going to do a bunch of examples in a second video. Okay?